So before we actually start, let me introduce you all to Women Who Code and our mission and vision. So let's have a quick glance on these things. So today as speakers, we are having Whitney, Divya and Vasu. They all are engineers at Zipline and they will be sharing their knowledge with us today. So this is our mission, and our mission is to inspire women to excel in technology and careers. And our vision is a world where women are representatives as technical executives, founders, VCs, board members, and software engineers. And our target is engineers with 2 or more years of experience looking for support and resources to strengthen their influence and level up in their careers. So we are having a strict code of conduct where we ensure that there is not any kind of discrimination and everyone will be treated equally. And we are very strict at this. Uh, in case if you think something wrong is happening or something is something is like that is not you are comfortable with on our portal, please feel free to report and fill this form, and we will look into that matter. So let's get started, and I hope you all will be very happy and excited for this. So over to speakers.
All right, thank you, Pavla. Hi, my name is Whitney, and today we're going to be talking about autonomous vehicles. So, as an introduction, I'm an embedded engineer at Zipline, and I'm from New Jersey. My background is actually in mechanical engineering at Princeton, and also I do flight operations at Zipline as well, in addition to coding. I love robots and I love building things that move.
Hi everyone, I'm Vasu. I'm originally from Mumbai in India. I have a PhD in computer science from Cornell in the US. And before Zipline, I worked at a bunch of self-driving car companies. It's really exciting for me to be here be here with you to talk about Zipline. I like coffee, crosswords, and making bad puns. So if a few slip out, you'll have to forgive me. And just like Whitney, I also like making things move using software.
Hi everyone, I'm Divya. I'm from Calgary, Canada, and I just finished up my electrical engineering degree at the University of British Columbia in Vancouver. Before Zipline, I did a couple internships at an autonomous helicopter startup and then working on drones at Boeing. I really like drawing music and trying to make my puns as great as Vasu's, but it's never gonna happen. I really like things that fly and being creative, and I think that designing brains for drones is the nice sweet spot in between.
Awesome. Thanks so much. So before we get started today, I want to kind of introduce the world of robotics to everyone. So when you think of robots, what comes to mind? Is it perhaps something that looks like this, like a humanoid, artificial intelligence, perhaps going to take over the world kind of figure? Or maybe if you're into Disney or Pixar, the things that you think of are more like WALL-E or Baymax. But these robots are, of course, like what the media represents robots as, and they can also seem really futuristic, unattainable, and something that won't really happen in our lifetime. But that's not actually true. There are actually robots all around us right now in our homes, like Roomba, the home vacuuming robot. And there's also robots on the streets, like this neuro robot who may come to a home near you sometime soon. So at Zipline, we actually take this at the next level. We build flying robots. So most of the world may know us as an autonomous vehicle company, but really autonomous vehicles is just a fancy name for robots. So some of the really cool technology we have at Zipline is basically how we perform these deliveries. So the whole mission of Zipline is actually we use these drones to deliver packages to customers around the world. And how does it work exactly? Our drones actually don't have any landing gear, so we can't take off and land like normal airplanes. How do we launch our planes? We use a high-speed catapult that launches our planes at over 100 kilometers per hour. And then once it's in the air, it flies and it reaches its destination, which is a hospital or health center where it delivers medical products via a parachute. And so you can see here that the package lands right on the ground, and you can see all the other packages that landed there too. So despite being a parachuted package, we actually have pretty good delivery accuracy. Now, this is my favorite part. How do our planes land? Because we don't have landing gear, we can't just take out the wheels of the plane and have it glide gently on a runway. What we do instead is we stop the plane from flying midair and we catch it out of the sky. It's pretty crazy to look at. The plane flies in and it catches onto this line and it swings down, ready to basically get recovered and torn apart by our flight operators. So what you see here, actually, here's a zoom in picture. There's a tiny centimeter long hook at the end of the tail that catches onto this line. It's pretty amazing to see. And this line, it pulls out and it actually slows down the aircraft, helping it land. So these are currently where we operate around the world. We are a global company and we operate in Rwanda, Ghana, and the US as of now, although we are expanding very rapidly. We deliver vital medical supplies all around the world to people who really need our services. And we provide an essential service to the places that we serve in, delivering products like blood, vaccines, and also COVID samples. So that being said, how does this all work? Well, going back to the fundamentals, what really makes a robot a robot? There are a few components that go into the hardware of the robot. So at the lowest level, you have the vehicle autonomy computer, which is where all of the math and the heavy computation happens. You also have the mission command, which is kind of like the controller. It's what tells the robot where to go. And so every robot has a mission. It has a goal at the end of the day, and it's trying to autonomously decide how to get there in the best way possible. So a few things that it needs to do that. One is the hardware interface, and these are the sensors that actually tell the robot where it is. In order to figure out where it's going, it actually needs to know where it is to begin with and how it's moving and things like that. Then it needs actuators, which will help it get to that final destination. In the case of our drones at Zipline, this will include things like GPS to tell it where its location is, and then propellers and motors to actuate it and to help it fly through the sky.
So if we were to zoom in on the vehicle autonomy box that Whitney talked about, we can think about the software that actually makes a robot autonomous. So all of it starts with sensor data, as Whitney mentioned, and the most important thing for the robot to do first is figure out where it is and what the world around it looks like. So we call that aspect of robotics localization and mapping. So if the robot has a sensor like GPS, it knows where it is in the world. And then if it has something like LiDAR or camera, it can look around and find obstacles and localize them as well. So if you look at the box in localization and mapping, you can see there's a robot with an arrow that points towards the heading that it's heading towards. And it has highlighted an obstacle around it in pink, and then also created a little radius around it in blue, saying, I want to stay 1 meter away from this obstacle. And it's doing all that via using sensor data and some fancy algorithms and filters to decide where the obstacles are and where it is currently located. And then as Whitney mentioned, every robot has a mission. So if you look at the top here, we have the mission command, which looks like an iPad with a map on it. And in the case of Zipline, that includes operators telling the drones to deliver to certain hospitals. In the case of a car, an autonomous car, that might be you telling your car what restaurant you're going to tonight. When you have this mission and then also your position and mapping, you can begin the motion planning process. So this whole green block here represents motion planning. And motion planning is really figuring out where the robot should go and how it should move to get there. So we usually split this up into two sections. One we call the global planner, and the other one we call the local planner. So the global planner acts as a rough course estimate of where you'd like to go. So that's why there's an image of a Google Map route here. As you can see, it's a set of rough lines that kind of tell you where to go. In the case of an autonomous vehicle, that might be the roads you take to get to a restaurant. In the case of our drones, that might be the route that you fly over some mountains and buildings to get to a hospital. These are generally also things that we can compute offline. For example, for Zipline, we get elevation models from governments and satellite companies that tell us exactly where there's mountains in Rwanda. So we can plan routes to go above and through these mountains to get to hospitals. So once the robot has a rough course idea of where it should go, unfortunately, it can't just start going along that path because there's a lot more constraints it needs to satisfy. So what the local planner does is it takes into account constraints of how the robot can move. So for example, our drones only have certain turn radii and certain acceleration limits. For cars, they might be able to turn in certain ways and not turn in others. I'm sure that some people have struggled with parallel parking and 3-point turns before. Robotics has to take all of that into account. So the local planner will come up with a path that the robot can truly take and also take into account any new obstacles it sees along the way. So for example, you can see that this purple block connects to the local planner block, and the purple block is dynamic obstacle detection. So if for example, autonomous car sees a human in its path, even though its global plan told it to go straight along this road, it needs to react. So the car will generate a new plan that still approximately follows the global plan, that will avoid this human, for example. So you can see an example of this in the block where you see a red path drawn around an obstacle. And the dynamic obstacle detection in this case is using computer vision to detect humans. So once we run through that process, we have a path that the robot can follow. We need to actually make this happen on the robot. So we implement something called a controller. A controller generally operates on position, velocity, and acceleration targets, and it sends out the actuator commands needed to get the robot there. So as you can see, like this whole system basically operates in a loop on the robot. So we'll localize ourselves, map all the obstacles around, create a plan, execute that plan with our actuators, and then repeat the process. And we keep doing this until we reach our destination. So that kind of leads me to introducing one of the biggest problems in robotics, which is how do we get to our destination? Like Whitney said, every robot has a mission and we need to figure out how to complete that mission. So this problem actually is applicable to many industries that isn't just robotics. We call it path planning. So for example, path planning can be something related to mapping out a route from, in this image, like Philadelphia to New York. But it can also be related to our drones, where we map out routes for drones to fly from our distribution centers to hospitals. So although these applications are very different, it's all path planning. Another example that is not robotics related, but shares a common problem is Uber and figuring out how to route Uber pools around the city. So if you have to pick up 3 people and they all need to go to 3 different places, you want to figure out the fastest and cheapest way to route your driver to do that. And then another example that brings it back to robotics is warehouse robots. So if someone puts in an order for a package, the warehouse robot needs to be able to navigate to that package in the warehouse. And all of these are ultimately path planning problems. I'll hand it over to Vasu to go into the computer science specifics of this path planning problem.
Okay, thanks, Divya. So let's talk about graph search. So for those of you who have been maybe doing practice interviews or interviews, a lot of the problems have to do with graph search, right? And so just for those of you who may not be as familiar, the basic problem setup is you have a graph, which is basically a set of nodes and edges that connect them. And you have a start node and an end node, and you want to find a path through the graph from the start to the end that only uses valid edges. That's the graph search problem. There are 2 basic flavors of graph search. So these are uninformed and informed search. And a lot of really simple graph search algorithms like breadth first search and depth first search are what we call uninformed, because they don't really use any information about the underlying environment of the graph. So the graph is constructed from some abstraction of the real world, and you just search on this graph without thinking about that original domain. In contrast, an informed search uses some information about what the graph represents. So as an example, if you have this 2D grid and you make a graph out of it by taking each cell and then connecting them based on some assumption about how you can move between cells, you can sort of use that property in the graph search. And specifically, the way you use it is by means of a heuristic function that you'd use to explore the environment efficiently. And we'll go into more detail on what good heuristic functions look like. But in this specific example, if your graph is this 2D grid and the actual path is sort of this 2-edged path, then a good heuristic might be the Euclidean distance between the start and goal node, even though you know you can't really get directly from the start to the goal node. Great. And the big advantage of informed search is that it tends to be more efficient in how it explores the graph. Great. So next, let's talk now about how this informed search perspective can be applied to motion planning. And specifically, we're going to talk about an algorithm called A-star that you may or may not be familiar with, but you'll be very familiar with it by the end of this presentation. Next, please. So just to sort of give you one more concrete example in the context of motion planning, the way you apply A-star to motion planning is you have a start and a goal node, and maybe you have some obstacles that indicate places that your robot is not able to drive or terrain it's not able to traverse. And what you're trying to do is find a path from the start to the goal node. And so this animation sort of shows you exploring the space in order to find a path. And if we give it just an additional couple of seconds, you'll find that it eventually finds a path around this obstacle. And so we'll walk through this in a lot more detail in the next couple of slides. Great. So it's time for some notebook shenanigans. So I'm going to share my screen, hopefully. Great. Okay. So we're going to go over A-star in sort of excruciating detail. I hope you're ready. So before we begin, I'm going to sort of set up the problem, set up the environment that I'm going to do this graph search in. And we're going to walk through the various components that are required. Great, so it's just some imports. Okay, so the first thing I'm going to do is, as I said, set up the start and goal and the grid that I'm going to search on. And so if you look at this code, I'll give you just a second to read it. It basically sets up a start and goal position, XY position in 2D in meters. We say our grid size that we use to discretize the continuous 2D space is 5 meters. We say the robot is about a meter in radius, which means that That's as far as we can get from any obstacle, right? We have to stay at least a meter away because the robot is about a meter wide. And then we just specify some range for this workspace. Okay, so if I visualize this, that's what that looks like, right? So you have this 2D grid. It's divided into grid cells. Each grid cell is 5 meters by 5 meters. And then this green is the green X is the start and the red one is the goal. Great. So I want to quickly describe a couple of utilities that we'll need. Since we're moving back and forth between position and index, we'll want some utilities for converting back and forth between them. And so we have these two utilities, calculate grid position and then calculate grid index, that convert back and forth. And they do a really simple transformation, right? They just say, well, if you're here, if you're at grid index X, Y, then in reality, you're at position something else. And just as a sanity check, you want to make sure that these two are inverses of each other. So if I have a position, if I have a grid, if I have a 2D position 1025, and I convert it into an index, and then I take those indices and I convert them back to position, I should get the same thing. And so you'll see that XY, the position, gets converted into indices 4 and 7. And then if we calculate the positions corresponding to 4 and 7, we get back the original. And these are just utilities that we'll use to compute on the graph and have that reflect the reality in the actual environment it represents. Okay, great. Just for completeness, to drill it into your heads, that's what that position looks like, right? So 10, 25 corresponds to grid cell 4, 7. Great. Okay, we're ready now to add some obstacles. And so the way I'm going to do that is I'm just going to go over some indices that some positions rather, sorry, that I've selected beforehand and say there's an obstacle here. And so I've added a bunch of obstacles specifically to make our lives easier. I've added a border to prevent our robot from running off the edge of the world. And then I've added these two obstructions that prevent the robot from directly just cutting a line from start to goal, just to make the problem a little interesting. Great. So the next thing we're going to define is the robot's motion model. And Divya talked a little bit about this, but a motion model basically describes how the robot can move on the graph, right? And so the way we are going to set this up is we're going to say that the robot can take one step to the left, one step to the right, one step forward, one step back, and it can also go diagonally. That's the motion model for the robot. If you look at the way I've set this up, there are 3 elements. So there's dx, dy, and cost. And so looking at just the first row of the motion model, this tells me that I can take 1 step x, 0 y, and the cost of that is 1. Similarly, on the diagonal, if I take 1 step like minus x minus y, the cost of that is square root of 2 because it's a slightly longer physical path. And so just to give you a visualization for this again, that's what that corresponds to, right? So I've just plotted arrows corresponding to each edge in the motion model. And so if the robot is at the center here, we're basically saying any of the 8 grid cells adjacent are accessible. Cool. Okay. So there's a few more components we need before we can delve into A star. And the first is an obstacle map. So remember that earlier I provided you with the specific locations of obstacles, but when we're doing the search on a graph, we really want to know at any point in time, at any node on the graph, whether or not that's in an obstacle. And so what we do is we take the list of obstacles, we take the 2D grid, and for every cell in the grid, we say, is there an obstacle or is there not an obstacle? And we create this sort of 2D map. And that's what's happening here. So we start out initializing everything to false, iterate over X and Y indices. And then if the robot needs to think that it needs to consider the specific cell as occupied, you know, taking into account its radius and everything, then we say true for that cell. So if we plot this out to distinguish between occupied and not, that's what we get. And you'll see that it's exactly this. It's just now per cell, you know whether or not that's an obstacle. So green here being free, red being I'm in an obstacle. Great. So now let's talk about the nodes of this graph. What are the nodes of my graph? Each node has an XY position in the grid It's an index into the grid. It has a cost that tells me how far away it is from, or how expensive rather, it is to get to this node from the start. It has an index, which is just some unique ID we assign to all nodes. And then it has a pointer to a parent. And the pointer to a parent will be really useful when we're eventually trying to get a path from the start to the goal. And I'll highlight that later. So just to show you what the index looks like, it's really just a unique numbering from 0 to 210 in this case. So for each grid cell here, we've assigned it a unique index, starting at the bottom at 0, and snaking upwards to 10. This is just a way to say, give me this node. So give me node 147. I know exactly what node you're talking about. Great. There's one more piece that we need before we start talking about the actual algorithm, and that's this notion of a heuristic. So we talked about heuristics when we were looking at the slides, and I said that we'd be using the Euclidean distance. And so that's what's implemented here. So if I have two nodes, I'm taking sort of the hypotenuse of the triangle defined, right? So the 2D Euclidean distance between the 2 points. To give you a sense of what that actually implies physically, this is a start and goal node, and I've sort of colored in each of the grid cells with sort of a darker shade here. A darker shade of red means it's closer to the goal, right? And so you'll see that there's this natural gradient moving towards the goal. And this is information we'll use when we're exploring nodes for the search. Great, so now we're ready to talk about A star, exciting. So the first thing we do is we initialize. And the basic idea behind A star is gonna be, you're gonna maintain two sets. You're gonna have a set of open nodes and then a set of closed nodes. You're gonna start by putting each new node you look at into the open set. Then you pull out the best node of the open set, meaning the node you think is most likely to be closest to the goal. You expand all of its neighbors using the motion model. So you say, if I'm at this node, here's where I can get to next. And then once you've done that, you put that node into the closed set because you've explored it. So we start off by initializing these two sets. They're empty. And then we initially add the start node to the open set. That's the first node that we're going to explore, because we know that we begin at the start. The tautology. Cool. So now everything I say from here on, we're gonna loop. That's why I have this big marker that says loops. Loop begins here. It's mostly for me. So once we've added the start node to the open set, let's sort of display the state of our search, because we'll do this periodically. So you'll see that the start node has turned yellow. I'm going to use this as an indication of it being in the open set. So yellow is going to mean open set, blue is going to mean closed set. So let's proceed. So the next thing we do is we select from the open set the node with the smallest total cost and heuristic cost. So I want to focus your attention on this line here. So we're selecting the min of the nodes in the open set based on this key, which is the cost of the node plus the heuristic to the goal. So you're saying, this is the cost it took me to get to this node, and now this is the projected cost to get to the goal. And you're taking the node with the lowest value of that. There's this one quantity, this weight applied to the heuristic. I'm happy to talk about it later if anyone is curious, but basically you select a weight that works. In this specific example, if I had a lower weight than 10, the search kind of took too long because we weren't exploiting the heuristic as much as we should. But we can definitely talk about how you craft heuristics if anyone is interested. Okay, so we're going to select the current node from the open set, which, surprise, surprise, we only have one thing in the open set. So the current node is also the start node, which is also the only thing in the open set. And I'm going to use the color magenta. This is supposed to be magenta. I'm going to use the color magenta to indicate the current node. Once I've done that, I check to see if the current node is the goal node, because if I'm at the goal node, I'm done, right? I know that I've found a path from the start to the goal because I started at the start. Unfortunately for us, that's not happened yet. So we didn't print found goal. So we'll continue. the next thing we do is we take the current node out of the open set and we move it to the closed set. And so as I said, that makes the node blue, okay? This will get a little more interesting once we have a few more nodes, I promise. Okay, great. So now that we've said, take this node, remove it from the open set and put in the closed set, what we need to do is expand all of its neighbors and add them to the open set so that we continue to expand outwards from this node. And so let me quickly walk over this code and then I'll show you what it's doing. So for each row in this motion model, you remember I showed you the rows of the motion model earlier. I first expand the neighbor that corresponds to applying that motion model in the current node. So for my current node, I say, let's take a step in this, let's take a dx dy step. And then I create a node with a cost that corresponds to the current cost plus the cost corresponding to that motion. So for example, if I take a step forward, I add 1 to the current node's cost. Once I've done that, I check to see if this new node, this neighbor node, is a free node or is it an obstacle. If it's in an obstacle, I know that I cannot move there, so I just throw it away and I continue with the next node in my neighbor set. But if it's free, then I add it to the open set. Specifically, I add it to the open set if it's not in the open set yet, but I also add it in if it's in the open set, but the cost that I've computed this time is lower than the previous cost. Because what that means is that I found a lower cost path to get to this node. And so I replace the previous path with this path. You may say, but where's the path? Like how is this happening? And this is why I want to remind you of the parent pointers. So basically every node contains a pointer to its immediate parent. And what you're saying by saying I've opened this, I found a node with a lower cost is equivalent to saying you found a path with a lower cost. Great. So let me show you what this process of expanding the motion model looks like. So you'll see that from the current node, the cyan X shows which neighbor I'm considering. And you see I've kind of iterated over all 8 neighbors and I've added them to the open set. The last one that's still cyan, it's been added also, it's also been added, but we also display the current neighbor. That's why it's still cyan. Okay, so that's what that looks like. I look at my current node, which is magenta, and I add all of the neighbors to the open set. And then I go back and I loop. So let's go back to where it says loop starts here and do it again. So I'm just going to print the current state. So now you have one closed node and a bunch of open nodes, right? Once again, I'm going to pick the best node to expand. And you'll see, interestingly, we've chosen as our current node, the node that is closest to the end in Euclidean distance. We could have chosen any one of the 8 neighbors, but because we have this heuristic, we've chosen the one that's closest to the goal. So that's one of the advantages of A-star is that using a heuristic, you're able to explore more efficiently by considering nodes in an optimal order. Okay, we're still not at the goal, unfortunately. So we move that node to the closed set. Again, we expand its neighbors, and now you'll see we won't add the neighbors that are in the obstacle, right? Because there's no point adding nodes that you cannot move to. Okay, so we've done that, and then I'm going to do one more iteration. We're going to go back and do it again. So the current state is now these are the 2 closed nodes. Here are all the open nodes. Again, we'll select a node to expand. This is not the goal node, I'm afraid. So we move it to the closed set, and then we look at its neighbors. And you kind of get the picture. Like the algorithm just continues until it finds the goal. You get the picture, but I want to give you the full picture. So this is kind of, if you run it for long enough, this is kind of what ends up happening. So you'll explore all the neighbors. You see the magenta current node being moved around, and then eventually you round the corner and you find the goal. So now you have a path from the start to goal, but what is it? We talked about parents, and so in this block of code, you see that we're basically walking backwards from the end, from the goal. We're walking backwards until we reach the start. And if you do that, then plot it, you have a path from start to goal. So that's an overview, excruciating detail of A star. And we're going to go back to the slides now. Thanks, Whitney.
Thank you, Vasu.
There's just a couple more. Yes. So I wanted to quickly address something that Divya brought up early on, which is, do robots really move like that? Like we have this grid and we said you can jump, one step to the left, one step to the right. And the answer is no, robots don't actually move like that. But the way you can make this work in real life is by constructing your grid such that you know that you can get your robot to move like that, right? Using this local planning approach that Whitney talked about, not Whitney, pardon me, that Divya talked about. And so you construct the 2D grid knowing that eventually if you have a path through the 2D grid, you have to make the robot follow it. Now, if you have kind of dynamic constraints on your robot, so the robot's motion is restricted, you may not actually be able to follow sharp turns in this grid. And so one thing you can do to remedy this, for example, is to construct your grid not in 2D, but in 3D, and more generally in ND. But if you think about the 3D example, including X, Y, and theta, which is the robot's heading in the grid, prevents you from saying, for example, that you can move from a position where you're facing this way to a position where you're facing this way immediately, because that's just not something robots can do. Typically, they have to make sort of smooth turns. One other thing you can do is what's called lattice-based planning. And what this means is that at any state, you know what the primitive motions are that your robot can take. So for example, I know my robot can turn left. That's, this is the precise trajectory that looks like. I know it can turn right. I know it can go forward. And I sort of characterize those motions using primitives. These could be sort of polynomial equations that describe the robot motion. And now I do graph search on a graph of these. So it's no longer a grid, but it's this lattice of primitive robot movements, like left, right, or maybe hard left, soft left, forward, hard, soft right, hard right. And now I'm doing the graph search on that. But the nice thing is once I've done that graph search, I know that the resulting path is something that my robot can actually follow in real life. So the last thing I want to quickly talk about is how this applies to Zipline. And so we talked about how we serve these large service radii in various countries. When we're planning paths for our zips, we call our drones zips. When we're planning paths for them, we use something exactly like the lattice-based planning approach that I described to you. So in the left side animation, you'll see this green graph, and then you'll see it get down selected to some red paths. And we've used A star to generate paths like this at Zipline. So that's one cool practical application. One thing I want to point out is that our paths are actually, they're in 3D, right? Because as you see on the right, we have to sort of ascend and descend, sort of climb and descend over these mountains and through these valleys in order to achieve those distances. So yeah, that's just one cool way in which we apply a core computer science problem to a robotics domain.
Cool. So one of the other things we wanted to talk to you folks about is ROS, because this is Vasu gave a great overview of robotics problem, a really important robotics problem, and we wanted to let you know how you could potentially implement this, on your own computer. So ROS is an open source robot operating system that lets you build on top of different hardware, like different types of robots, with plug and play software packages. So ROS will actually include everything that makes the robot work. So the controller, the navigation, all of the path planning and the simulation tools required. And then your actual computer will run regular OS level tasks like memory management, scheduling, and web browsing. So the way that ROS works is it uses a client server model and a publish subscribe message passing layer. So you can essentially have a simulation that's publishing sensor data, and then you can have a robot that's subscribing that data. And then you could have potentially like a computer vision node that publishes like data about where obstacles are. And then you can have a motion planning node that subscribes to that data and runs algorithms. So this system really lets you plug and play software. So we wanted to show you a demo in RAW so you could see what robotics looks like in practice. And this is something that you folks can get started with on your own. I'll be using a tool called Ignite Robotics. It lets you run all of this in your browser, and they have like courses and things like that that you could follow. So in the demo, you'll see a window on the left that is basically displaying something called RViz. And RViz essentially visualizes what's happening in the robot's brain. The robot's brain displays plans, what we call cost maps. So this is a map of all of the obstacles that the robot sees, and robot movement itself. You'll also see a green line that describes the global plan, outputting from the global planner that I talked about at the beginning of the presentation that will actually be using A*STAR. And then you'll see a local plan in red. On the right-hand side, you'll see something called Gazebo, which is the simulation environment that Ross uses. And the simulation environment feeds the robot sensors and displays the robot's movements in real time. So I'm gonna go ahead and share my screen so you guys can see this demo. Okay, so like I said, here are the two windows. This is our car, autonomous car here with some cones around. This is the RViz, and what I'm going to do is I'm going to give this robot a 2D nav goal by clicking where I want it to go. So I'm going to click right here, and you'll see that this robot did a graph search with A*STAR, and it actually created this green path. And you can see it's got sharp turns and such, but then the red path is the local planner that is able to plan to the final destination. So this is kind of just a sneak peek into what robotics, prototyping, and actual system building can look like. You might be spending some time working with cool simulations like this. If you'd like to go back to the slides, Whitney.
Cool, awesome. So thank you, Divya, for that presentation. And up to this point, we've kind of only seen the theory behind it, the math behind it, and even though Divya showed us a beautiful autonomous vehicle, it was still a virtual vehicle on a screen. So how does this really work in the real world, and what kind of constraints are we dealing with? So intuitively, one might think, oh yeah, of course, there's the mechanical components, there's electrical components, there's a lot beyond just the software. But actually these constraints also inform how we design the software itself. So to break it down into very broadly the components of a robot, as we mentioned earlier, on board the robot is a microcontroller, typically, which are the brains of the robot, sensors like GPS, cameras, other things, and actuators, the things that make it move. Oftentimes you'll see robots, like in the case of Roombas, they're nice and small and compact. Sometimes they're larger vehicles, like we saw, like the autonomous vehicles, and also sometimes they're planes that fly in the sky. And so each of these robots have their own size, weight, and power constraints. Power being actually a component that people may not really think about intuitively, but it's super important, like how much battery life you have, especially if it's an electrically operated vehicle. You don't want to consume too much power, otherwise its lifespan will be very, very short. So because we're limited on the size, weight, and power, we also are limited in terms of how much compute we have. These problems that we're introducing are actually really, really challenging problems that people today are solving using big computers, maybe stacks of computers of really, really powerful size and really like heavy in terms of power consumption in the cloud, like in AWS. But these are problems that we actually need to solve on board a small robot. So we sometimes only get compute as small as the palm of our hand. And this actually lends itself to many creative challenges. Not only are we solving difficult problems, but we have to solve them in a creative way such that we don't take up too much memory, power, and other resources. So in the case of Zipline, actually, we may have only small portions of the map at any point in time, and we are constantly updating our own information as we go. And this is one way we can save space and do things faster with the limited resources we have.
Thanks for explaining that, Whitney. Some of the real world constraints are what makes robotics really exciting and fun to work on. So now that we've given you a bit of an intro to robotics, some of you folks might be wondering how you can get involved. I think if you're still in school or not in school, robotics clubs and competitions are a great way to get started. I personally started with robotics through a cube satellite design team at my school, and that really launched my career in this field. And online courses are really great as well. I personally took some edX and Coursera courses that helped me out a lot. And I just mentioned the environment that I was showing you a demo on was through something called Ignite Robotics. And then another one is to prototype in ROS. It's freely available to everyone to use, and it's a great way to deeply understand the robotic stack. And a cool thing about robots that makes us proud at Zipline is that one of our founders, Keenan, was actually on the founding team of ROS and helped really build out this amazing open source system that anyone can use to get into robotics and build a real system. Lastly, one of the best ways is to work at a robotics company like Zipline. A lot of teams actually make this magic happen, and you can find your spot within robotics in many different ways. For example, like what Whitney works on, embedded software. I personally also did internships in embedded software before I started getting more into autonomy. You can work on software infrastructure. A lot of the things we work on require a lot of compute and infrastructure to actually take out into production. You can work on autonomy and controls, which is what Vasu and I work on. Also machine learning and perception for computer vision and like sensor data consumption in general. There's a lot of need for data science. We have folks that look at metrics from our flights and figure out what kind of things the robot should be doing better. Full stack engineers help with simulation and UI UX design for interfacing with the robot. So at Zipline, we have flight operators that have iPad apps that they use to launch the zips and give them like commands and things like that. That leads me to operations and testing. Whitney mentioned that she works on flight operations as well, and it's a cool job because you get to be very hands-on with robots and you'll get to see them moving in the real world. And then we also always need mechanical and electrical engineers as well in robotics, so that's a good way to get involved with robotics and help make the hardware of the robots work. So thank you so much for listening. We had a great time presenting to you folks, and we'd be happy to take any questions if you're curious about anything. And yeah, thank you.
Hi, thank you so much, Divya. We actually have questions in the chat, in the Q&A section. Would you like to take those?
I'd be really excited to take a couple of, I'd be excited to take a couple of the questions about A-star. I think I can answer them all in one go. So there are a few questions and I'll just knock them out. The first is, what's the difference between A-star and SLAM? So A-star is a path planning algorithm or a motion planning algorithm. SLAM is simultaneous localization and mapping. And so the way we've described it, this use of A-star would happen after you've localized and mapped, but also during, right? Because as you're doing simultaneous localization and mapping, you're moving around whatever estimate of the environment you have. And to do that, you might be using something like A-star. One thing that's interesting is that A-star, the algorithm itself, may be used within SLAM algorithms separate from path and motion planning. So it's actually quite a nuanced question. But the fundamental difference between what we've presented and SLAM is that this is something that could apply even once you have a map. It could apply on a known map and with sort of known precise positioning. But it could also apply on a map you're still building and when your location is uncertain. There are certainly ways to do that. So a couple of other questions. What are some other ways to optimize the gradient? I'm assuming this refers to the heuristic. I did say that I would talk about the heuristic. And the follow-up is, can new techniques like representation learning be used? Yeah, so coming up with a good heuristic is certainly one of the biggest domains where any kind of learning is super, super helpful. Handcrafted heuristics work really well in cases where you know what the interesting features are of the domain, but where you don't really know, as humans, we don't really know what's interesting about the domain. Using representation learning or machine learning in general can be really, really helpful because the heuristic is often not something that's obvious to humans, but a computer can very easily figure it out. Then there was one other question. Oh yeah, this is interesting actually. I've been doing some work in quantum computing. It's really exciting. Using computers like D-Wave, you can find a path easily. Is that something you've considered? And maybe the drone can send a request to a quantum computer. So we have not considered sending requests to quantum computers yet. But if I recall, just from my knowledge of what quantum computers are really good at, they're really good at unstructured search, right? They're really good at the type of search where you really have to look at all paths. In domains where you have a heuristic, I'm not really sure what the state of the art is for quantum computing, because when you have a really good heuristic, that reduces the worst case complexity of A-star a lot from the usual n squared or n to the d. And so, yeah, that's a good question. We have not looked into that in detail, but it would be interesting. And then there's one more question, which is, could you explain again how the line is drawn where the end node is going back to the start node? So one of the guarantees of A-star is once you find the goal, once you've explored and you reach the goal, you're guaranteed that the current path is the optimal path, just because of the order in which you're exploring the nodes. And in order to achieve that guarantee, you actually need one property that I completely glossed over, which is that you need this heuristic function to fulfill what's called admissibility, which means that it needs to underestimate the true cost to the goal from any node. And in the case of a grid, typically if you use Euclidean distance, you're definitely going to be underestimating because any path you really take has to zigzag. So as long as you have an admissible heuristic, you're guaranteed that when you reach the goal, the path you have will be the optimal path. And you can just walk backwards over the pairs. Cool. Divya and Whitney, you want to take some of the other questions?
Sure. I see a question about my favorite drone or robotics project. I mean, my favorite drone project has been working at Zipline. I've been working on cool algorithms that help our drones avoid each other in the air. So that's been really interesting because we send sometimes we send 10 drones to the same delivery site and they all fly the same path to get there. So they need a way to make sure they don't collide with each other. So that's what I've been working on for the last 4 months or so of coming up with an algorithm to make them avoid each other. I see a question about microcontrollers, so I'll hand that over to Whitney, the resident embedded genius here. So,
Divya, could you read the question to me? I can't actually see questions while I'm presenting.
Yeah, sure. So what kind of microcontrollers do you use at Zipline?
Yeah, we use a collection of microcontrollers actually. We use SAMI 70s and TMS 570s. So the TMS 570 we use for the more compute heavy processes, and the SAMI 70s are kind of the more general purpose ones. We actually have 10 nodes throughout our entire vehicle, which may seem like a lot, but they're really, really important for redundancy on our vehicles. we're flying through some pretty gnarly conditions, including like thunderstorms and rain. Our drones do not take a break at all. So we've flown through thunderclouds, which have actually released static electricity into our planes and caused nodes to reboot in flight. So having that redundancy, at first when we were designing it, we didn't really know that like what would happen, but we knew that having this like level of redundancy would be important eventually, and it turned out to be vitally critical to our operations and keeping our planes in the sky as much as possible.
Cool. This next question is about the recovery system. So Whitney, if you could scroll back up to that GIF, it might be nice to have playing in the background. Someone said that they really like our drone landing method, and they're wondering how often drones miss the line when they're trying to land. So the interesting thing about the problem with recovery is that this system needs to figure out exactly when to snap its line taut such that it can catch the zip's tail hook. So back in the day when this system was first implemented, the zip would always miss the line. Like it was almost a given. And then slowly as people rolled out improvements, we got up to 70%. And now we have like a 99% catch rate or something along those lines. And a lot of that has come from improvements in communications and then also onboard filtering and like GPS localization. So the reason this whole system works is the drone is communicating with this like recovery system and saying, this is where I'm at now, this is where I'm at now. And the recovery system actually estimates exactly when its wings will be past its line so that it can snap up and catch the drone at the perfect time. And I think basically the team did a great job of tuning this system over time to the point where it's incredibly reliable and pretty beautiful to watch every single time. It never gets old.
Yeah, I want to add a few things too. I remember seeing this question. It was definitely inspired by aircraft carriers. Actually, in the early days of Zipline, the recovery system wasn't this tall. It used to be very low to the ground, just like an aircraft carrier. And when the zip basically caught onto the line, it would flop onto a bouncy castle, like a big foam mat, essentially. So it was pretty silly to see, but you know, Zipline has come a long way and has like iterated through a lot of different versions of what this looks like today. So it's pretty amazing to see it come together today. Yeah.
There's a question about how weather conditions affect drones. You want to take this one?
Yeah, sure. I can elaborate a little bit more. I mentioned earlier that thunderstorms and flying through thunderstorms have actually caused problems on our vehicles before by discharging static electricity. Over time, we've really like tried to dissect these failure modes and try to like basically improve our aircraft to be more robust to them. So in the case of the thunderstorms, like we didn't realize that at first, but as soon as we did, engineers added more like ground planes on the wings, which would actually like route the electricity out of the like electronics and to other locations around the body, so we could be more resilient to that. I actually think static is one of the biggest problems that we face, especially in a lot of the dry environments that we fly in. Another one is heavy winds. Airplanes today even can't fly in highly turbulent conditions, so our planes also, being smaller, are even more susceptible to big windstorms and will sometimes, I guess, like have a quote-unquote crash landing. It's not actually a crash. We actually deploy a parachute if we detect something's going wrong. So for us, like as a company, safety is always the #1 priority. And so every time we develop a product, we have the safety of the people in mind, and we never want to put anyone in harm's way.
I'll add one thing from, sorry, Divya. I'll add one thing from software perspective, which is wind also cause us to be blown off our paths, these paths that I showed you early on. And we have, as Whitney said, since safety is paramount, we have a lot of checks in place that will parachute a vehicle if it's blown too far off its path. So that does happen if we have gusts, massive gusts of wind.
Yeah, Vasu, that's exactly what I was going to say. Like one of the biggest things that we're concerned about is a downdraft where the wind pushes the plane down and it can't climb back up. And this is detrimental because as Vasu showed you, the path planning we do is done with digital elevation models. So we've like computed our paths so that we fly over mountains and fly over obstacles. And if now there's wind pushing us down off of our path, we can't guarantee that we won't collide with things anymore. So that's one of the situations in which we would pull a parachute.
There's one question that's really exciting. It's, do you have any branches in Canada, and does Zipline offer summer internship opportunities? We definitely have summer internship opportunities. They're on our website. If you go to the careers page, several teams are hiring interns. As for having a branch in Canada, Divya, do you want to speak to working from Canada for a little bit?
Yeah, sure. So the team is very global. I worked remotely from Canada for about 4 months before moving out to California, and it was a great experience for me. The nice thing about Zipline is it's mature now, so there's a lot of infrastructure that allows you to test things remotely, even run your own flight tests remotely. So we kind of like support basically employees all around the world, including Canada. I see a question that says, how has COVID impacted drone deliveries? I think for our work and our distribution centers, all of us have been taking the necessary COVID precautions. But specifically, Zipline actually delivers COVID test samples now in Ghana and North Carolina in the US. So this is a really exciting thing that we started working on because a lot of governments and health institutions saw the value in being able to deliver things on demand, including COVID tests. So because of this, we have special protocols that flight operators and like people at the distribution centers need to take. So for example, at one of our distribution centers, there's a separate kind of shed building area where all the COVID samples are handled, and people are in full PPE when they're doing anything related to COVID samples. But in general, COVID has actually exacerbated a lot of problems in the health industry and has revealed problems that can potentially be helped or like fixed by Zipline. So in that sense, we're grateful that people are actually putting effort into improving global health systems. There's another question that says, what does maintenance on the zips look like? Whitney,
I can take
do you
this.
want to take that?
Yeah. So zip maintenance is a really interesting question. So our vehicles are actually broken up into parts. They come apart. Just kind of a fun idea for a plane. So there's 3 main components. There's the battery, there's the wing, and there's the body. So operators can actually move each of these parts separately, which is really, really convenient often because they'll assemble these parts on the launcher when we're getting ready for flight. And if a single component has a problem, we can just swap that one out really quickly. Like for example, if there's a sensor on the wing, such as like the air data sensor, and it's faulty, an operator can go and just swap that wing really quickly without having to like, take apart the entire vehicle or like swap it out with a whole new one. And this way, it actually makes it really easy to do maintenance. There's a goal on the mechanical team. I'm not on the mechanical team, but the goal is basically every part swap on the entire vehicle should be done in less than 5 minutes. And so there's spares of every part at every one of our distribution centers, and they're pretty much like Legos. Like you just unscrew and rescrew, and it's back in operations. So it's pretty fun.
And also a cool thing about what Whitney said is that the batteries are also like plug and play Legos. So anytime a zip goes and finishes a mission, we just take out its battery and stick a new one in and charge the other one while it's flying. So we don't have to worry about like charging the entire drone as a whole. There's a question here that says, how does Zipline calculate the cost per flight of a zip to Zipline? Yeah, so I think that there's a lot of really smart people on our finance and reliability team that actually come up with these numbers and crunch these numbers. But internally, we do have a simulation that lets us simulate what a delivery order day would look like. Like we can say, okay, at one of our distribution centers in Ghana, what does a day of medical supply orders look like? And then we can come up with, if we have 10 drones there, how many orders could we actually fulfill in that day? And this kind of helps us figure out, considering like the fixed cost of how much our drones cost, and then the fixed cost of how much it takes to build a distribution center, we can figure out ultimately what the cost per flight ends up being at different places. And the team takes special care to actually target a cost per flight. And this informs the mechanical engineering team to design new sorts of planes, and it also sets goals for the entire team so that we can make the system more efficient and cheaper.
I want to just add to that there are other costs that are important as well, not just the cost of one flight, as Divya mentioned. I mean, the cost of a single flight is a really great metric, especially considering the lifetime of a single zip, et cetera, but something we think a lot about is the cost of enabling new services, right? So the cost of bringing up a new delivery site, how do we get that down? How do we make it cheaper to onboard more customers and serve more customers? So that's another thing that we do extensive work on, is bringing that cost down, making it cheaper for us to serve more people, basically.
Okay, I think we are done with questions, right?
Yeah, feel free to move on to the presentation, Bhavna.
Yeah, sure. So here are some of our upcoming events. You can check it out on our website. And these are some very interesting things which is ongoing on WWCode. And we are having a beginner study Python group where we are having sessions and we discuss general Python things and some interesting things. And one more session we are having ongoing, that is NLP session. So you can join us for this. And these are the links where you can have access to all our upcoming events and sessions. And feel free to connect with us and share our knowledge, and will help us to grow together. And I want to thank you all. Thank you to all speakers who are and Zipline for this amazing experience, and we all will be glad. And this is very insightful and very interesting thing. So thank you all. Thank you all for joining.
Thanks for having us.